The two most common temperature scales used in the world are Fahrenheit and Celsius. This is a picture of Gabriel Fahrenheit. He was German. This is Anders Celsius. He was Swedish. Both of them developed their temperature scales in the 1700s. Fahrenheit was the first one to build a mercury thermometer, so he built the best thermometers of his age. The Fahrenheit temperature scale is now only used in the United States. The Celsius is used in the rest of the world. Celsius has some logic to it. It made 0 degrees C the freezing point of water and 100 degrees C the boiling point. So it's sometimes called centigrade, 100 degrees between boiling and freezing. Fahrenheit, there's a lot of debate on the history of that. But the suggestion is that he made 0 the coldest temperature that appeared in his hometown of Danzig. In his scale, 32 degrees is freezing, and body temperature was originally thought to be 96 degrees. Water boils at 212 degrees Fahrenheit. Not a real logical scale for our modern day. Here's a typical room temperature in Fahrenheit, 72 degrees. If I change it to Celsius, it's about 22 degrees Celsius. There is a conversion you can do, I'll show you, but it's much better to just have a feel for the temperature scales. Room temperature is always going to be around 20 to 25 degrees Celsius. I'm putting the temperature probe now in ice, and you can see it is in Celsius approaching 0. So 0 is the freezing point of water in the Celsius scale, the melting point of ice. In Fahrenheit, it's approaching 32 degrees. In the less logical Fahrenheit scale, water freezes at 32 degrees. A third temperature scale that is unfamiliar to most people is the Kelvin temperature. This is a picture of Lord Kelvin. He was a British lord. His real name is William Thomson. And he lived in the 1800s. So his temperature scales developed in 1848, 100 years or so after Fahrenheit and Celsius. His scale is the most scientific yet, based on the laws of thermodynamics. You can also see that he lived in a time when the first photographs were invented. So we're going to learn about this temperature scale, which is the most useful for doing science. In the Kelvin scale, the melting point of water is 273 degrees. So this is a Kelvin temperature. Kelvin temperatures are much more useful in science than are Fahrenheit or Celsius. All the gas laws that we're studying will use Kelvin temperature. Here I have water on a hot plate beginning to boil. These bubbles here are H2O vapor. Many students mistakenly believe that's hydrogen and oxygen gas, but no, it's water. It's just hot enough water to break its hydrogen bonds and become a gas. Now I'll put the temperature probe into boiling water, and you can see we quickly get towards 100 degrees Celsius. In Fahrenheit, this is approaching 212 degrees Fahrenheit. In Kelvin, we're approaching 373 degrees Kelvin. If you're thoughtful, you'll realize that the Celsius and the Kelvin temperature differ by 273 degrees. This is mathematically useful. Here we can see the data from your Alchemist Cookbook plotted. These are the actual data points out here. 1, 2, 3, 4. Then this red line extends that. It's called extrapolation. Extrapolation. Going beyond the points. Extra means beyond. You can see that this goes down to a value here, which would give the gas volume 0. Clearly there can't be a volume less than 0, so this must be the coldest temperature conceivable. The coldest temperature conceivable. So this very cold temperature here, which is the lowest temperature that can exist, is negative 273 degrees Celsius. That is sometimes called absolute zero. Coldest possible temperature. So what that really means is no molecular motion. The kinetic energy of the molecules goes to 0. You can't get any colder than that! Exclamation point. Here we have the same data, but replotted using Kelvin temperatures. The Kelvin temperature has great advantages over Celsius or Fahrenheit. Here in this scale, absolute zero is 0. 0 Kelvin is the absolute coldest temperature, which we've defined as absolute 0. That's where kinetic energy is 0, molecules cease to move. So now you can see every number will be a positive value. How warm is it? Well, the kinetic energy of the molecules is above 0, so the temperature is above 0. This scale has great advantages mathematically. If you look here, here's actual data where we have about 300 degrees Kelvin, 300 Kelvin. The volume is 1 liter. So I'll write it this way. It's not precisely 300 Kelvin, but for the purposes of this graph, it's fine. What happens if we cut the temperature in half? That would make the temperature 150 Kelvin. You can see that the volume now is half. 150 Kelvin. Half a liter. Isn't that convenient? You half the temperature and you half the volume. It is proportional. I think you can see that if we extrapolated the line, we would eventually get to 2 liters, double the volume, at about 600 Kelvin. So this is the advantage of Kelvin. The volumes are proportional to Kelvin temperatures. You need to be able to convert Celsius to Kelvin to use this well, but we do that simply by adding 273. For example, 100 degrees C, just add 273, is equivalent to 373 Kelvin. And that allows you then to use the convenience of the scale, do proportions. It's the way to go.